Hello everyone, my name is A. Dabuli Reddy from CSC AIML A section. Today, my Tech Talk topic name is Development of High Temperature Superconducting Transformers for Railway Applications. Introduction. After the discovery of high temperature and superconduction and the availability of the first HTS tapes for use in windings, different groups all over the world began working on the development of HTS transformers. What all these projects have in common is that they are aiming at stationary applications. The advantages of stationary HTS transformers compared to transformers with normal conductivity are well known and are described in detail. In contrast to this, our activities are aiming at creating a mobile application on electrical rail vehicles. In Europe, 15 kilowatt 16.7 Hz or 25 kilowatt 50 Hz. These vehicles contain oil-filled transformers with windings made of copper or aluminium. Due to greater requirements for lightness and compactness, the conductor carries considerably high current densities, typically 6, than in case of stationary applications, typically 2. The achievable efficiency, typically 92% to 95%, is therefore sustainably lower in the case of stationary transformers, typically 99.5%. Because the transformer has adhesive influence on a vehicle's energy consumption, the use of HTS results in a saving amounting up to approximately 30% of all the driven system energy costs involved in operating a vehicle. The efficiency is raised to over 99%, whereas the weight and volume can be reduced by approximately 45%. These figures include the cooling system, because a weight and volume reduction is generally to be considered more important on vehicles than in stationary applications. The considerable amount of energy and the generally applicable advantages of HTS transformers are indicated, and strong motivating factors for the development of HTS traction transformers. The main aim of the project was to evaluate the future feasibility of HTS traction transformer for 16.7 Hz and 50 Hz frequency. These are some pictures. Design of 1 MVA transformer subgroups. Ratings. The single-phase transformer has a nominal frequency of 50 Hz. It has two identical LV windings taken towards the outside. The HV winding has a nominal voltage of 25 kilowatt and a nominal current of 40 ampere. The LV windings have a nominal voltage of 3089 volts and nominal current of 360 ampere. The nominal impedance voltage is 25%. Core and coil assembly. The core and coil assembly consists of a two-limb core whereby each limb is wound. The winding structures of the two limbs are identical except for the direction of winding. The windings are arranged in a doubly centric layout in the radial sequence. The HV windings of the two limbs are connected in parallel. The inner LV winding is connected in series with the outer LV winding at the lower end. Core. Because the core is placed in liquid nitrogen and therefore contributes to the cold losses, a high quality plasma treated type of sheet with thickness of 0.23 mm and specific loss of 0.85 at 1.70 and 50 Hz was selected in contrast to 1.5 in conventional traction transformers. Conductor. BI 2223 tape was made in 1999 by Vacuum with a pure silver matrix, and a silver magnesium sheet was used as conductor. The tape consists of 55 filaments and is not twisted. A conductor length of 6.7 kilometers, representing a mass of 54 kg, was used in the windings. This length has a width of 3.65 mm on average and thickness of 0.258 mm. HV winding. HV1 and HV2 each consists of a stack of 9 identical coils, each stack having 224 turns. The individual coils are connected in series by means of a top to top, bottom to bottom intercoil connection, and total number of turns is 2016. A single insulatable tape is used. The mean winding diameter is 312 mm. LV winding. The inner and outer LV windings are layer wound, each with one layer and 56 turns per layer. At the end, the inner and outer windings are connected to each other in series. The LV windings taken to the outside, therefore, have a total number of turns of 112. The already mentioned transposed conductor is used. The inner and outer LV windings have a mean diameter of 234 mm and 385 mm respectively. Leakage flux iron. The leakage flux iron is a complex periodic structure made up of air gaps in iron sheets with the size of a centimeter square. It increases and guides the leakage flux outside the HTS tapes so that the leakage flux into the tapes closest to the leakage gap is 72 MT, which is considerably less than that in the leakage flux iron. The leakage flux iron has total mass of 140 kgs. Liquid nitrogen container. The LN container is made of stainless steel and its volume is optimally matched to the core and coil assembly. During nominal operation, it contains 250 liter of liquid nitrogen with a mass of 200 kg. The inner and outer dimensions are 420 mm, 832 mm, 1200 mm, and 430 mm, 842 mm, 1245 respectively. Its mass is 272 kg. Vacuum container. A conventional oil tank from the traction transformer series PR424 was used as the vacuum container in order to save time and cost and to gain experience with realistic mounting conditions. The interior dimensions of the oil tank are 461 mm, 980 mm, 2950 mm. It is considerably longer than necessary. Optimization of the volume was dispensed with. In order to make the oil tank vacuum tight, stiffeners were fitted. Wiring and current leads. The electrical connections between the HTS windings in the LN container were made of solid copper. As well, the connections from the HTS windings to the bushings of LN container. The bushings of LN container were connected to the bushing of vacuum container and solid copper bars. In the vacuum chamber, nearly the LN container, there is a line section for which the ratio between the length and the diameter was dimensioned so that losses occurring on the low temperature side are minimal for nominal current. Cooling systems. The cooling systems contain of a 4-cylinder Stirling gyro generator, an electric motor, a coupling cryostat, and control cabinet. In order to save time and money, the cold head was not optimized for 66K. At 77K, the refrigerating capacity is 4000 watt. At 66K, it drops to 2500 watt. Instrumentation. The core and coil assembly contains 20 temperature sensors, platinum 100, two of which are on the core and 9 in each winding arrangements of the two limbs. Assembly and cool down. Test results. Pre-test, measurement of impedance voltage and load loss, measurement of no load loss, and no load apparent power are the 3 points while doing the test. Conclusion and outlook. After the plan to develop a 1 MVA HTS transformer was completed last year, the engineering documents are now being drawn up to build a full power onboard transformer with. A planned follow-up project envisages construction, assembly, stationary and mobile tests, and testing of the new pioneering technology of a superconducting railway transformer on a trail vehicle. So this is the use of a superconduction on railway applications graph, and it's been increasing from years. And some examples of high temperature superconductors. Electronics, basic research. In electronics, we can find sensors, supercomputer. Cryoelectric components. In basic research, high field magnets, squid sensors, bolometers, particle detectors, and in medical techniques, squid diagnostics, magnetic resonance, imaging, MRI, microwave techniques, filters, antenna, resonators, delay lines, active components, and in power engineering, generators, motors, transformers, current limiters, switches, cables, energy storages. For traffic engineering, magnetic transport system, ships, engines, and maglev trains. These are some examples of superconductors. Thank you.